Hi everyone, welcome to our session on machine learning lectures. I am Dr. Andrey Holz, and today we are going to cover 4 interconnected topics that are absolutely critical for anyone serious about applied machine learning. It's cross-validation, hyperparameter tuning, pipelines, and AutoML. So let us get started. And here's a quick look of what we'll be covering today. Cross-validation. We'll see why splitting our data multiple ways helps us get a more reliable measure of a model's performance, rather than relying on a single train test split. Then we'll go to hyperparameter search. We'll dive into how adjusting the right parameters like learning rates or tree depths can dramatically boost our results, and we'll explore popular methods like GridSearch and Randomized Search. Then we'll go to ML pipelines, and we will learn how to organize data transformations and model training into a single workflow, making our code more efficient and less prone to errors. And then we'll go to AutoML. We'll see how automated frameworks can tackle tasks like model selection and hyperparameter tuning, potentially saving us a lot of time and effort. Of course, every technique has trade-off, whether it's the computational cost of intensive searches or the interpretability changes of complex pipelines. We'll discuss those as well. And finally, we'll tie it all together with a wrap-up, so you'll leave with a clear picture of how those concepts fit into robust real-world machine learning workflows. Let us get started. And before going further, it is important to understand where this topic fits into the broader context of the CRISP-DM process, the standard for data science. Normally, this is part of the modeling and evaluation. Sometimes it's also part of the deployment. I believe we're ready. Let us move on. So you might wonder, why do these topics matter? Well, imagine you train a model on your dataset using a simple train test split. And you tweak a few things and you get an accuracy of 95%. And you feel great. Until you deploy the model and discover it performs terribly on real-world data. That is exactly the kind of scenario these techniques helps us avoid. By applying proper cross-validation, we get a far more reliable estimate of our model's true performance. By tuning hyperparameters systematically, we ensure we are not leaving performance gains on the table. By using pipelines, we make our workflows consistent, preventing data leakage or forgetting to apply transformations to our test data. And finally, AutoML can automate some or all of these steps, giving us a baseline or a powerful final solution. Without these techniques, it is incredibly easy to overfit, misread the accuracy metrics, or spend hours chasing suboptimal solutions. And now we'll see how each of these methods fit into a strategy for building better machine learning models. Let us get started. Let us start with the Bayes cross-validation. What exactly is cross-validation? Well, at its heart, cross-validation is about getting a more stable and accurate estimate of a model's performance than a single train test split would provide. Instead of training on one big chunk of data and testing on a small leftover chunk, we rotate through multiple subsets of the data as our training and validation sets. The most typical variant you'll encounter is K-fold cross-validation, but there are a lot of other strategies. So the key takeaway of this is, with cross-validation, you reduce the risk of overestimating or underestimating how well your model will do on unseen data. Of course, it is more computationally intensive, but it's a worthwhile trade-off for more trustworthy results. So let us take a look at several approaches that will help you. First, let's talk about this K-fold cross-validation. And Let us use 5 as our, say, number. We take our data set and split it into 5 roughly equal parts. For each round, we use 4 of those parts for training and the remaining 1 part for validation. We repeat this process 5 times so that each fold gets a turn as the validation set. In the end, we average the performance across all 5 runs. This approach helps us get a more reliable idea of how our model might perform on unseen data, compared to just one random train test split. That's the most basic and the most simple approach. And we are moving to the stratified K-fold. It's like regular K-fold, but with an important twist. It respects the class proportions in each fold. For instance, if your dataset has 20% of its labeled in class A and 80% in class B, each fold in stratified K-fold will also have about 20% of class A and 80% of class B. This is especially beneficial when we have imbalanced datasets. Without stratification, we might end up with some folds that have too few positive examples, leading to misleading performance estimates. Leave one out cross-validation takes the idea of K-fold to the extreme by letting each individual data point be its own fold. So if you have 100 data points, you'll train 100 separate models. Each time you use 99 points for training and the remaining one for validation. It provides the most thorough use of data, but it is also the most computationally expensive, and the results can have quite high variance because each train validation split only differs by a single point. And there are also advanced techniques that are used for time series splitting. There are also nested cross-validation to get the unbiased hyperparameter tuning comparisons, and of course repeated K-fold to reduce variance. Let us take a look. When our data has a time component, like stock prices, weather data, or sensor logs, randomly shuffling it for standard K-fold would be a mistake. We could end up training on data from the future to predict the past. Time series cross-validation fixes this by splitting the data chronologically. Each time we train on a block of earlier data, then test on the later slice. This ensures our validation step mirrors a real-world scenario, making predictions about the future based on the past. And there are two big options, is the expanding window and sliding window. And the window size and the window type is a hyperparameter here, actually. So you could also find the best fitting window size and window type. Nested cross-validation introduces two layers of cross-validation. The outer loop is for the final evaluation. The inner loop is where we tune hyperparameters. By keeping those loops separate, we ensure our final performance metric isn't tainted by the same data we use to tweak the model. This is particularly important if you are comparing multiple models or want a truly unbiased estimate of how well a tuned model will perform in the real world. It is also can be used when comparing multiple model families like random forest versus SVM versus XGBoost because it ensures a fair comparison. Each model is tuned independently in the inner loop, then evaluated on fresh data in the outer loop. And after completing nested CV, you typically end up with multiple best models, one per outer fold. You can average or analyze their hyperparameter settings to see which parameters were most consistently chosen. And let us move on. Repeated K-fold takes regular K-fold and runs it several times with different random shuffles. For instance, you might do a 5-fold cross-validation, repeat it 10 times, and average all 50 performance scores. This repetition helps smooth out any oddities from a single partitioning of the data, giving you a more stable estimate. However, be mindful of the added computational burden. You are effectively doing multiple rounds of training for each repeat. What about cross-validation for non-standard cases? What if we have something more complicated than just a binary classification? For instance, if we have a multi-class cross-validation and it deals with a dataset where we have more than two classes like A, B, and C, potentially with imbalanced distributions. A common issue is that a standard K-fold might accidentally create folds, missing one of the classes entirely. By using stratified K-fold, we keep class proportions consistent in every fold, giving us a more reliable performance estimate. If we have grouped data like multiple observations per patient, then leave one group out ensures each patient only appears in one validation fold. Finally, do not forget to look at metrics like macro, averaged F1, or confusion metrics. They will highlight exactly where the model might be struggling instead of just giving you a single accuracy score. Because again, this is a multi-class. What if I have multi-label? Multi-label cross-validation becomes necessary when each example in your dataset can have multiple labels, like an image that might be tagged both as cat, outdoors, dog, tree, whatever. And standard stratified cross-validation cannot handle multiple labels at once. So we look at iterative stratification. It maintains label distribution across folds. Another approach is binary relevance, where we effectively split the problem into multiple binary classification tasks, one per label, and then aggregate the results. And for evaluation, consider Hamming laws or micro-macro averaged F1, because you're no longer dealing with a single label per sample. And these metrics give a more accurate picture of how well your model performs across all the possible label combinations. And when we're switching from classification to regression, we deal with continuous targets, like a house price or sales forecast. If the data is independent and identically distributed and not too skewed, just use standard K-fold and that will be fine. However, if the target distribution is heavily skewed or has extreme outliers, we can create bins of the target values and then do a stratified-like approach to keep folds consistent. And of course, if the data has a time component, such as stock prices or any time series data, we use time series split so we do not accidentally train on future data to predict the past. And finally, keep an eye on metrics. They each paint a different picture of how well your model is capturing the underlying relationship. So let us sum up what we've learned about cross-validation. We can compare different approaches. So K-fold is our go-to method for general machine learning tasks where data is independent and identically distributed. Its main advantage is simplicity and efficient data usage. Each fold gets a chance to be the validation set. However, it is not well suited for time series because that would break chronological order, and if we naively use K-fold for classification, we risk unbalanced splits unless we stratify. Stratified K-fold is a perfect fit for classification tasks with imbalanced classes. It preserves the class distribution in each fold, helping us avoid skewed or missing classes in any particular split. The downside is that it does not directly extend to regression or multilabel data unless we do some extra steps like binding or iterative stratification. Repeated K-fold is helpful when we have a small dataset and we want more robust estimates. We simply repeat the K-fold process multiple times with different shuffles, then average the results. This lowers the variance for our performance estimate. The cost, however, is increased computation because we're efficiently running K-fold multiple times. And it also doesn't solve issues for time series data. Time series cross-validation is specialized for chronological or forecasting problems. Instead of random folds, each fold is defined by sequential time block, ensuring the validation data always occurs after the training data. This way, we do not accidentally train on future information. The trade-off is smaller training sets each time, and we often need more folds to get stable estimates. Leave one out cross-validation makes each data point its own test set. This is very thorough. We use n-1 samples for training and one leftover sample for testing. And we repeat it n times. It also maximizes our training data usage in each run. However, it is extremely computationally expensive for larger data sets because we have to train n models, and the results can be high variance when each training set differs by just one sample. Nested cross-validation is the gold standard for model comparison and hyperparameter tuning. It uses a cross-validation loop inside another cross-validation loop. The inner loop tunes the model. The outer loop tests it. That way, we get an unbiased performance estimate of our tuned model. The downside is that it is computationally heavy. We are effectively doing cross-validation within cross-validation, and it can be more complex to implement. But if you are comparing multiple models or want a truly robust metric, it's often worth the extra effort. So, to sum up, each technique has its own advantages and disadvantages. The table here gives a quick overview and quick reference, ideal use cases to help us choose the right method, pros to outline benefits, and cons to warn us about potential pitfalls. Just use this table if you're stuck. And we're moving to our next topic, and it is a hyperparameter optimization. Let us take a look at it. Let us firstly clearly define what hyperparameter optimization is and why it is critical. A hyperparameter is any setting that configures how your model learns or is structured, like depth of a decision tree or the learning rate of a gradient-based method. Unlike the learned weights in neural network, these hyperparameters aren't discovered automatically during training. They must be chosen manually or via a search process. This matters because different hyperparameter values can drastically change our model's performance. For example, overly large max depth in a decision tree might cause overfitting, while a too shallow tree might underfit. Relying on defaults may not align with your data or objectives. That is why we use hyperparameter optimization, like GridSearch, RandomSearch, or Bayesian Optimization, to systematically try out different configurations and find the settings that best maximize accuracy or minimize error or give you the best metric. Well-tuned hyperparameters can make the difference between a so-so model and the state-of-the-art performer. Grid search is the classic approach, great for small parameter spaces. But as you add more parameters or broaden their ranges, the number of combinations explodes. Randomized search often finds similarly good solutions in less time, making it a popular choice for large or complex parameter spaces. And this is the illustration of it. Let us compare two of them. In grid search on the left, we systematically sample points across a predefined grid for each parameter. Notice how we treat all parameters as equally important, creating a full combinational grid. This can be very inefficient when only a subset of parameters truly matter. Most of the grid points end up exploring less impactful dimensions. In random search, we randomly pick parameters values from specified distribution. We don't systematically cover each combination of parameters. Instead, we spread our efforts more broadly and, crucially, have a better chance of hitting values in the important parameters range. This is especially helpful if one parameter dominates performance while others have smaller effects. This graph shows that grid search might waste resources exploring values of a parameter that isn't very influential, whereas random search lets us probe more diverse points in the search space. The key takeaway here is that random search often finds good hyperparameter settings faster for high-dimensional or partially relevant parameter spaces. However, grid search remains easier to interpret for simple or lower-dimensional problems. What about Bayesian optimization? Well, it iteratively refines its guess on performance landscape. And after trying one set of hyperparameters, it updates its probabilistic model and suggests potentially better configuration. This can be extremely powerful when each model training is expensive and you want the best results with fewer trials, but it still relies on chance. Let's take a look at the comparison graph here. On the right, we see how Bayesian optimization progresses in a more direct way compared to grid and random search. With grid search on the left, we sample a uniform grid across the parameter space, even if many of those points aren't near the true optimum. Random search, in the middle, places points more spread out and has a decent chance of landing closer to good regions quickly. But it is still a chance-based guess. Bayesian optimization, however, uses an underlying model, often a Gaussian process or a tree-based method, to approximate our objective function, like model accuracy, and decide where to sample next, each time refining its guess about the best region. Notice how in the Bayesian panel the sequence of blue squares is moving from lower left towards the top right, eventually converging on the orange star, which represents the best known optimum. This adaptive, data-driven approach means we typically require fewer evaluations of our expensive model compared to brute force or purely random sampling. That is why Bayesian optimization is especially valuable when each trial, such as training a large neural network, takes significant compute time. On the downside, it can be more complex to implement and interpret than a standard grid or random searches. But if you're looking to find that spot quickly with minimal wasted effort, Bayesian optimization is often the go-to method. And let us take a look at some popular tools for hyperparameter tuning. First is scikit-learn. This is the foundation of many Python ML workflows. It includes GridSearch and Randomized Search, both easy to integrate with scikit-learn pipelines. You can define your parameter grid or distribution and let scikit-learn handle the cross-validation loops. The next one is Optuna, a more advanced library focusing on Bayesian optimization. It is known for its user-friendly API and supports hyperparameter pruning, like early stopping, and great visualization tools. And if you have a model that takes a long time to train, Optuna can save you a lot of compute by adaptively searching the space. RayTune is designed for scale. It can run many trials simultaneously on a single machine or a cluster. That is particularly handy if you are dealing with large datasets or expensive model training. And finally, HyperOpt uses the tree-structured Partition Estimator (TPE) for Bayesian optimization. It's a solid balance between simplicity and advanced search. Many people start with scikit-learn's built-ins, then move to something like Optuna, RayTune, or HyperOpt when they need more sophisticated or scalable optimization. In short, these tools let us move beyond the guesswork and systematically find hyperparameters that maximize our model performance, whether we're tuning a simple logistic regression or large ensembles on a distributed cluster. But what are the use cases? Hyperparameter optimization isn't just about squeezing extra accuracy points in a lab setting. It drives real commercial value. For instance, a well-tuned fraud detection model can block fraudulent activity without frustrating too many legitimate customers. In predictive maintenance, precisely tuned algorithms can spot early signs of machinery failure, potentially saving thousands in downtime. Recommendation systems become far more effective and profitable when hyperparameters are dialed in to deliver personal relevant products or media. Meanwhile, marketing teams can more accurately identify customers that are likely to churn if models are carefully optimized. Even classical time series forecasting like a RIMA or Profit benefit from hyperparameter optimization, leading to more efficient demand planning in retail or logistics. Across these domains, hyperparameter tuning directly correlates with better performance, lower costs, and improved user satisfaction. And let us talk about some practical tips for choosing hyperparameters effectively. First, identify key hyperparameters. Not all parameters have the same impact. Things like learning rate in neural network or max depth in a tree can drastically change performance, whereas some minor parameters might only bring marginal gains. Next is progressive tuning. Start broad, explore a wide range of values or distributions, and then narrow down once you see which areas look promising. Think of it like zooming in on a map. Proper validation is crucial. Always tie hyperparameter tuning into cross-validation so you are not overfitting to a single train test split. And always keep a separate final test set to confirm your chosen hyperparameters truly generalize. Log experiments along the way. Tools like MLflow or weights and biases help you record which parameters you tried, what results you got, and how long each run took. This makes it much easier to reproduce or revisit successful experiments later. And most importantly, mind your budget. Tuning can be expensive in terms of both computational resources and time. You don't want to lock up the entire server for days running an enormous grid. And finally, use domain knowledge. If you know certain parameters are more influential in your field, focus on those first. And this combination of strategy, resource management, and expertise leads to the best possible model performance. A machine learning pipeline is a series of sequential automated steps used to pre-process data, train models, and make predictions. It provides a systematic framework to handle the complexities of machine learning workflows, ensuring efficiency, reproducibility, and scalability. On this image, you can see the typical components of the machine learning pipeline. And it all starts with the data ingestion, like you gather the data from various sources, databases, API, files, whatever. For example, you collect user activity logs from a web application. Then you have data validation, meaning that you validate that the data is good and you have all the data in place and you follow all the protocols for the data. And then you have the data pre-processing. You clean, normalize, and transform the data into a usable format. Like you handling missing values, encoding categorical data, scaling, and removing outliers. For example, using standard scalar in scikit-learn to normalize the data. And then you have the feature engineering. You generate, select, or transform features to improve the model's performance. And here the techniques include feature selection and feature transformation. For example, adding some new feature by combining age and salary. And then you have a model training, meaning you use algorithms like linear regression, random forest, or whatever to train a model on the data that you processed. For example, you're just using random forest classifier to predict customer churn. And then you have a part of the model analysis where you have evaluation, validation, and hyperparameter tuning. For the evaluation, you run the model on the evaluation dataset and check the performance. For the validation, you validate the results, you validate the metrics, you use cross-validation to ensure the results. And then you also have the hyperparameter tuning. You optimize model parameters using like GridSearch, RandomSearch, or Bayesian Optimization. For example, you're finding the max depth and number of estimators for a decision tree. And then you have a model packaging and model publishing, meaning that you're preparing the model to be stored in the model registry. And then you have a model deployment. You integrate the model into the production systems to make predictions on real-world data. For example, exposing an API to classify customer queries. And then you have a monitoring and maintenance to continuously monitor model performance and retrain when necessary due to data drift, like detecting drops in accuracy when the input data distribution changes. Normally, the typical ML pipeline is not that big. Normally, it is limited by the model creation, but sometimes you can have these big, really complicated, super automated ML pipeline. Imagine you're building a workflow that involves scaling your data, maybe applying some dimensionality reduction, and then training a classifier. You could call all these transformations step by step in your code. But what if you forget to scale your test set or do transformations in the wrong order? That is where pipelines come in. A scikit-learn pipeline lets you chain together multiple processing steps like standard scalar, PCA, and like random forest classifier into one unified object. When you call pipeline, it automatically does everything in the right order on your training data. When you call pipeline predict, it applies the exact same transformations to a test data before generating predictions. This dramatically reduces the chance of mismatch between training and testing transformations, also known as data leakage. Another advantage is how the pipelines integrate with hyperparameter tuning. Instead of separately tuning PCA's number of components or random forest's max depth, you can define a parameter grid that references each pipeline step. For instance, PCA number of components and classifier max depth. Then your GridSearch or randomized search will treat the whole pipeline as a single estimator, testing different transformations and model parameter combinations seamlessly. Ultimately, pipelines keep your code clean, your transformations consistent, and your tuning process simpler. Many efforts in ML projects come from applying transformations incorrectly to your train and test sets. And pipelines as an elegant way to solve this. Let's take a look how a simple pipeline in scikit-learn works using Iris dataset as our example. First of all, we import everything we need: the dataset, the model selection, the pre-processing, the pipeline itself, and the estimator, like random forest classifier. We load the data, we split the data into train and test, and then we define the pipeline. So we'll have the scaling part, the pre-processing via standard scaler, and the classification part with the random forest classifier. We define the parameters, and then we apply the grid search of the whole pipeline. We find the best parameter, and then we get the best possible score of the best possible pipeline, since we already know the optimal number of estimators. Scikit-learn pipelines is one of the key tools for classical machine learning pipelines, and we have already reviewed it, so that's just that simple. Another key tool is MLflow, and it's a powerful tool for tracking and managing your machine learning experiments. Instead of manually keeping notes about which hyperparameters or models we tried, MLflow lets us log these details automatically. In the example code on the right, we open an MLflow run, and with MLflow start run, train a random forest classifier, then call MLflow APIs to record our model, parameters, and final accuracy. Everything, like the number of estimators and the trained model file, gets tracked in MLflow dashboards. Why use it? Well, because in a real project, you'll do countless experiments. You will tweak parameters, switch models, or try different data pre-processing steps. MLflow keeps all these runs organized, so you can compare results side by side and easily revert to a successful model version when needed. It also integrates nicely with scikit-learn, so if it's already building classical ML pipelines, adding MLflow's logging is straightforward. And tools like MLflow save you from chaos of scattered nodes and naming conventions like model v5 final 2. By systematically logging each experiment, you can maintain reproducibility and keep a clean record of what works best in your pipeline. And our third key tool is Apache Airflow, which is all about orchestrating more complex ML workflows. If you are dealing with multiple steps like data extraction, pre-processing, model training, and evaluation, Airflow helps you manage them in a directed acyclic graph or DAG. Each step becomes a node in the DAG, and Airflow handles the flow from one step to the next. Why use it? Well, because beyond just training a model once, you might need to schedule daily or weekly runs. And Airflow lets you define and monitor these pipelines effortlessly. You can set up tasks like pre-process or training and specify their order. If one step fails, Airflow will notify you or automatically retry. The key features include scheduling, so your pipeline can run on defined interval, and monitoring, so you can see if tasks succeeded or failed in each stage. This automation is especially helpful in production environments, where you want to update your model or rerun data preprocessing regularly. And in short, Airflow is the glue that ties all your ML tasks together. It ensures each piece of your pipeline runs in the right order, on the right schedule, with a robust error handling. This is great for large-scale ML projects where a single script or notebook just isn't enough. And let us talk about AutoML. You might wonder, what if I treat the model selection, the feature selection and feature generation as a big pipeline and use the idea from the pipelines and from the hyperparameter optimization? Just consider everything as a hyperparameter. While this brings you to AutoML actually. AutoML stands for Automated Machine Learning. Its goal to reduce or even remove the guesswork from building machine learning pipelines. Instead of you manually deciding whether to use random forest versus XGBoost or how many layers your neural network should have, AutoML tools try out many possibilities automatically. They test different algorithms, tune hyperparameters, and sometimes even attempt feature selection or engineering. Some of the most widely used frameworks include AutoScaLearn, H2O AutoML, Tport, and others. The pros are clear. You save a ton of time, especially for large search spaces where, it's really hard to guess. AutoML can also discover pipelines combinations you might not have thought to try. Of course, there are cons. First of all, it is computationally heavy. You could easily spend hours or days letting an AutoML tool go through all the possibilities in your dataset and find the best one. Second, it can be a black box. You might end up with a pipeline that is hard to interpret or replicate by hand. And third, domain expertise still matters. AutoML won't fix badly collected data or save you from poor feature choices. Overall, think of AutoML as a powerful assistant. It can find strong baseline models or even final solutions, but you must keep an eye on interpretability, computational cost, and data preprocessing. There are many tools available for AutoML. There are open source tools, enterprise tools, cloud tools, and among popular frameworks is H2O, AutoML, AutoScaLearn, and Tport. Those are great for developers who prefer customizable and self-hosted solutions. On the other hand, cloud-based platforms like Google Cloud AutoML, AWS SageMaker Autopilot, and Microsoft Azure AutoML provide fully managed environments with a focus on scalability and simplicity. For enterprises, tools like DataRobot offer advanced capabilities for interpretability and deployment. And selecting the right tool depends on your specific needs, data size, and technical expertise. And this is the example of AutoML code with H2O AutoML. Basically, it looks similar to the pipelines and to the cross-validation schemes, pretty straightforward. And now let us have some demos. Hey everyone, today we're going to walk through a complete machine learning workflow using two datasets, the wine dataset for classification and the California housing dataset for regression. We'll cover key techniques like cross-validation, building pipelines, tuning hyperparameters, and using AutoML with H2O. Our main goal is to follow best practices to avoid data leakage, ensuring our models perform well on new unseen data. The first step is to set up the environment. We'll install the necessary libs like scikit-learn for our machine learning tasks and H2O for AutoML functionalities. Then it's just standard NumPy, pandas, scikit-learn. We're importing all of them, nothing special. Section 1, this is the classification demo. And for this, we'll use the wine dataset. This dataset is great for classification because it includes chemical analysis of wines from 3 different Italian places. We'll load the dataset and extract the features X wine and the target and the target labels Y vine. Let's check out the size of our dataset and see how the classes are distributed to make sure we're not dealing with any class imbalance. And here we can see the distribution of classes. Well, we might consider this is a pretty balanced data set. Again, we'll split the data, enter the train and test in order to have everything at hand. And we can see that since we're using the stratified split, the proportions remain. And now we're using the cross-validation. First is the K-fold cross-validation, the most common one and the most, let's say, simple one. It repeats 5 times, so each fold gets a chance to be in the validation set. We will also use the stratified K-fold. It is similar to K-fold, but ensures each fold has the same class distribution. We'll take a look at leave one out and just leave one out. And just for the purpose of the curiosity, we'll take a look at the time series split. However, it is not that important here. It's not typically used for the wine dataset, but well, it's good to know how to use it. And we'll also use the repeated K-fold, and we basically repeat the K-fold process multiple times with different splits. So let's take a look how everything goes. As expected, the K-fold, the classical K-fold, is the fastest one. It takes 1.5 seconds. Then, well, the stratified K-fold takes a bit longer since it ensures the stratification. Leave one out. The longest one, 32 seconds. Like, it's a huge time difference. But as we know that leave one out is just taking one and using it as a test. Time series split is pretty fast. It's actually pretty fast, and yeah, it only uses three splits actually, so that's why it is so fast. And repeated K-fold is again similar to the classical K-fold, so it's not a big deal. Let's take a look at the pipelines, and here we can use the scaler, the feature selection, and the random classifier as steps of our pipeline. So basically it's pre-processing, feature engineering, and classification. And we define the param grid in order to use the grid search and our scoring accuracy. And well, we just use the whole pipeline since it's the GridSearch CV. We use pipeline and we feed everything and we find the best parameters of the whole pipeline. It takes 16 seconds for the whole pipeline. And that's basically it. This is how you can use pipelines and cross-validation in order to use it. Let's take a look at the regression demo. By the way, we're not using for this simple classification AutoML since the wine dataset is too small for the AutoML, but we will use AutoML for regression. And for regression, we're using California housing. And California housing is pretty big. This dataset contains information from California, including features like median income, housing median age, and total rooms, as the goal is to predict the median house value in different districts. Again, nothing special. Get the data, we get the features, and we get the target. We split the data in order to separate it on the train and test sets. And yeah, we can then apply cross-validation again on the train set, on the big train set, in order to have the test set for the later comparison. And here we can have K-fold cross-validation, repeated K-fold cross-validation. We can use other types of cross-validation here, but it will require us to apply binning and some other sophisticated techniques, but for the simplicity we'll skip this. And here you can see that for the bigger data set, the K-fold cross-validation takes 54 seconds and 91 seconds for repeated K-fold. And for regression tasks, K-fold and repeated K-fold are commonly used. Time series is like reserved for temporal data to maintain chronological order. It is not usually used for the simple regression. But let's take a look at the pipelines. So we apply scaling and just random forest regressor here. So yeah, again, we can use the GridSearch, and that's pretty it actually. So since we do not have a lot of parameters, we can use the GridSearch here. And as for the AutoML, we utilize H2O. For this, we prepare the data set and like this, and we have a predictors, like defined predictors as feature names of the data set and target. Then we just use AutoML. We define the max runtime, the seed, the metric, and we define the project name in order just to have named. Let's take a look. Here we have time taken 61 seconds in order to parse the data, and we have the leaderboards. A lot of models were trained with different metrics, and the best model performance was the stacked ensemble. And this is how you can use the H2O AutoML to run it. So thank you for your attention and have a nice day. Hi, let's take a look at the hyperparameters optimization tools. We'll review Optuna, Hyperopt, scikit-optimize, and classical scikit-learn, GridSearch, and RandomSearch, Randomized Search CV. So we will use the diabetes dataset in order to reduce the complexity. We'll just use the one that already exists in the scikit-learn. You will also need to install Optuna, Hyperopt, and scikit-optimize. First of all, get the data, split the data into train and test, and we'll use just the random forest regressor. We define the param grid for GridSearch and RandomSearch, the space for Hyperopt, and the Bayesian search space for scikit-optimize. We start with the GridSearch. This is pretty straightforward. We already have seen how to utilize it. Just define GridSearch CV, define parameters, estimator param grid, and here you go. It takes 67 seconds for this data set, so pretty fast, I would say. Then we have the random search. Again, it has the similar interface as the grid search, since they're both from scikit-learn. Nothing special here. You just have this and you utilize it. And yes, it takes less time. Oh, we have the Hyperopt. Here things began to look interesting. We need to define the objective. The objective contains of classifier, or we have regressor here, so and score. And we also initiate the trials object in order to have this. And what we utilize here, we have max evals of 50, 50 tries. And yeah, we define the function. It has the objectives, the space, and the trials and parameters also. Yes, and we can later fit and check the best fitting. It took more than a minute, 82 seconds. We found the best parameters. Yeah, we will review the scores later. And here we have the Optuna. The syntax here is similar to the Hyperopt. So yeah, we define the objective, we define the model, define the score as a cross-validation score, and Optuna minimizes by default. We will create the study and measure the time and find best params, and then validate the best params here. Just for you to notice, we fit on train and predict on test. Keep this in mind. And also, yeah, we use train for scoring. What else? Yeah, Bayesian search. We define the Bayesian CV here and fit it. Well, the syntax is pretty straightforward, I would say. Yeah, it took more than the rest, but still, it's pretty interesting approach. For the large data sets, it would take less time. So let us compare what we have, like the RMSE here and the R2 squared. It looks like the models are pretty similar, I would say. So the R2 score is pretty same around all of them. And RMSE here, again, just the fluctuations here. So you can choose the one optimizer that you like. Personally, I like Optuna. It is super useful, pretty fast, so I recommend using Optuna. And that's basically it. So thank you very much and have a nice day. Welcome back. What are the key takeaways of today's lecture? As powerful as these techniques are, they come with pitfalls if you're not careful. One big danger is overfitting to your validation set when you do repeated hyperparameter searches. It's tempting to run a ton of parameters tweaks until you get the metric you want, only to discover your final model doesn't generalize. Always keep a completely separate test set or use nested cross-validation for unbiased performance estimates. And another issue is ignoring compute constraints. If you do a giant grid search with 10 different hyperparameters, each with 10 possible values, well, it's a lot of combinations, and it won't be possible to run quickly. Be strategic. Start with a smaller space, use random or Bayesian methods that converge faster. Also, track everything you do. Tools like MLflow or weights and biases let you log hyperparameters, metrics, code versions, and more. This ensures you can reproduce results and see what you tried. My advice: start small, pick a few parameters you suspect matter most, like a random forest, max depth, learning rate, reproducible, and whatever. Then expand your search if time and compute allow. Finally, always keep that final holdout set and verify that your best hyperparameter combination truly works on unseen data. And this is how you maintain interpretability and integrity in your results and avoid fooling yourselves. Wrapping up, we started by discussing cross-validation, which is critical for stable performance estimation. Then we moved to hyperparameter tuning, expanding how methods like GridSearch, Randomized Search, and Bayesian Optimization can significantly boost your model's predictive power if used correctly. Then we saw how pipelines unify all the transformations and training steps under one consistent framework, ensuring no data leakage and simplifying hyperparameter tuning. And finally, we reviewed AutoML, which aims to automate much of this process by searching across various models and hyperparameters. If you want to dive deeper, I highly recommend checking the documentation of the tools and build something based on it. And that is it for our session. At this point, I hope that you learned something new, and if something needs more clarity, please reach out to me. Thank you for joining. And as you move forward in your ML journey, remember that quality data, solid validation, and structured workflow are the building blocks of success. A well-tuned model isn't just about high accuracy. It's about confidence in how that model will perform on new data. Now you have a powerful toolkit, from choosing the right cross-validation strategy for your dataset to building reproducible pipelines, and even using AutoML if you really need it. And don't afraid to experiment. ML is as much an art as it is a science. I encourage you to take the techniques to your own projects, whether it's like assignment or Kaggle competition or real-world data, and continue to learn, adapt, and push the boundaries of what is possible. And thank you for your attention and enthusiasm. Keep exploring, keep innovating, and I look forward to seeing the models you'll build.